clouds here, and I couldn't recognize the other windows in previous years. So we know that's ongoing. Our commitment, our pleasure to work with the professors, to work with the research students to support the activity. So let me ask you another question. How many of you have attending, or plan to attend Professor Amoy's Nonlinear Optics courses? Awesome. So I don't need to make any more introduction. I know this is the third lecture, but I would suggest that probably you don't know. Professor Boyd is also a bridge builder. How many of you know that? A bridge builder. He's building bridges between the physics department and the electrical engineering department, between the American Physics Society and the IEEE. He's a bridge builder between the academia and the industry. He's a bridge builder between Rochester and Ottawa, between the United States and Canada. I don't know how much you can help on the politics, the understanding of politics of the two countries, but he's a huge bridge builder. So with that, we all benefited, the whole society benefited, which goes back to the IEEE motto. Our motto is we make the technology for the benefit of humanity. So Professor Boyd is one good example of that. So without further ado, let's welcome Professor Boyd for the last lecture on the Nonlinear Optics for this distinguished lecture series.
Thank you. I'm really quite honored that you would actually want to hear me more than once, but 3 times is just outstanding. By the way, I sat on Siri and she was complaining. If you heard that, she was not happy that I sat on her. So it's a real pleasure to be able to speak to you again. Now, truth in advertising. That's not the title that we announced. And it's because at the beginning of the semester, we announced 3 titles. And last night I realized that I had already covered all the material that was announced for today's lecture. So I panicked last night. I realized I did not have a talk to give. So I put this together. It's 2 separate topics. First is quantum imaging, and the second is self-action effects in nonlinear optics. So let's get started at this. So let me talk about quantum imaging. This is not very bright. You can see it, just barely. So here's the prospectus. Everybody has a table of contents. I need a different word. Prospectus. First of all, what do I mean by quantum imaging? So let's take a look at that. So the goal of quantum imaging is produce better images using quantum methods. Well, what do we mean by better? Well, here are a few examples of how an image could be better. Maybe you can form the image with a fewer number of photons. Maybe you can achieve a better spatial resolution, and maybe you can achieve a better signal-to-noise ratio. If you have a low contrast scene, signal-to-noise ratio might be the key issue here. Another way of expressing this is to say that quantum imaging exploits the quantum properties of the transverse structure of light fields. When I say quantum imaging, I will even include things like states of light that carry orbital angular momentum. They really mesh together. And I found this humorous. This was a mail order catalog that was very popular 20 years ago. Its name was Sharper Image, but that's maybe one of the least sharp images that you could imagine. Is that why they went out of business? You never know. Okay, so, but just to set the stage, even though we said that quantum imaging involves multi-transverse mode fields, let's just remind ourselves what the quantum properties are of a single transverse mode field. And I'll talk about quantum metrology. Quantum metrology means measuring things carefully. And imaging, well, you want to determine some property of an object when you form an image of it. So I like to think that quantum imaging is a subset of quantum metrology. So let's start looking at these features. And here are some of the examples of quantum metrology: squeezed light, twin beams, entangled light fields. And let me just quickly introduce some of these concepts for you. I think we've seen this slide already. It was maybe in my first lecture. This is just meant to remind you that the process of parametric down conversion, which is illustrated here, can be used to form two entangled photons. So this is one type of quantum state of light that can be used for metrology. I'll show you why as the talk goes on. But there's something else you can do. You can form what is called squeeze states of light. There are people in this room whose PhD thesis involves forming squeeze states of light. So how are the two related? So let's go back one slide. If you adjust this crystal, the orientation, so that the signal and the idler photon are both emitted in the forward direction and overlap with one another, then, well, there's some quantum coherence between these two photons. And if you go through a mathematical analysis, which we will not do today, you find out that the noise properties of the generated field are profoundly changed. To understand this, let's look at quantum states of light in the complex electric field plane. If you look at a vacuum state, there are things called vacuum fluctuations. I mean, even though the light has no photons in it, there will be fluctuations in the instantaneous field amplitude. And you can ascribe shot noise to the presence of these vacuum fluctuations. You can ascribe spontaneous emission to the presence of these vacuum fluctuations. So, but if you perform this sort of operation here, you find that this uncertainty ellipse, instead of being a circle, becomes an ellipse. So this is what you mean by squeezing. The noise properties are squeezed. It is more noisy in this quadrature. It is less noisy in this quadrature. So if you are clever, you can make your measurements using homodyne detection, and you can choose to look at this quadrature here, which is less noisy than even the vacuum state itself. So this, let's see, it was Dick Slusher who first demonstrated squeezing. But the first person I know of to have used this in the context of metrology was the group of Jeff Kimball. I think he was still at Texas. Jeff Kimball was Rochester, then Texas, and then Caltech. So here was the idea. He has two cells. One of them, the phase difference in going through this cell is slightly different than the phase shift in going through this cell. He takes his laser beam, he puts a square wave on it, and he wants to see how accurately he can measure the phase difference between this path and this path. If he does not use squeezed light, well, he sees a big signal, but there's this much noise on it. If he used squeezed light, this is really tricky. He injects the squeezed light into what classically would be the irrelevant issue. This is the unused port of the interferometer. He injects squeezed light into here, and he gets less noise here than he got in the first case here. So this is a way of thinking about things. Why do you have noise? Because vacuum fluctuations sneak in to this port of the interferometer. If instead of letting vacuum fluctuations sneak in, you inject squeezed light into this port, you end up with lower noise in your measured signal. Okay, now there's something else you can do. Very similar setup, but now crank up the intensity of your pump beam a little bit more so that these become reasonably intense. We call these twin beams. Well, they're formed in this process here again. Every photon formed here, you have exactly one photon formed in the other beam. So they will have identical fluctuations. Each beam itself is noisy, but the two beams fluctuate synchronously. So if you adopt a good measurement strategy, you can once again make measurements with better accuracy. And the group of Claude Fabre at University of Paris was one of the leaders in this. And well, here's his setup. Here he's doing this in the context of spectroscopy. He's tuning his laser through a potassium vapor, trying to measure the strength of the resonance. When he does this with laser light, he gets this level of fluctuations. When he uses twin beams, he uses this level of fluctuations. He gets this level of fluctuations. What he does is he just measures the intensity fluctuations of one beam and uses it in a feed-forward sense to perform the measurement with higher accuracy. Okay, so that was just a real quick reminder. Now let's talk about quantum imaging. And let's see how these tricks can be used to enhance the properties of an image-forming system. Here are just a bunch of names. Misha Kolobov, he was our visitor last summer, as some of you might remember. John Dowling has been in Ottawa for at least one of our quantum conferences. Claude Fabre has been here. I don't know. These are all my friends. They're my friends because they have such good taste in choosing their research topics well. First paper that I know of that talked about quantum imaging in this context was the paper of Misha Kolobov and Prem Kumar, Northwestern University. And, well, they said, let's choose the dimensions of our nonlinear crystal so that these signal and idler photons are emitted not just into one spatial mode of the field, but into many spatial modes of the field. And then they do that same trick that Jeff Kimball did, but they do it with an entire field of view, multi-spatial mode field. They have one detector here, and can more accurately determine the features of this object. Sort of. Well, it was a theory paper. It was a theory paper. They spelled out how to do it, and maybe they were ahead of themselves. It was at least 10 years before anybody actually managed to do this experiment. They're my good friends, so I can tell a story. It's sort of sad this is being taped. But Prem Kumar didn't bother to ask Misha if he was an experimentalist. He just assumed that this guy was an experimentalist. He brings him to Chicago to do this experiment. Misha says, well, I can work out the theory of anything. So that's why it's a theory paper. I think they still talk to each other. There's a misunderstanding. Okay, there's something called quantum lithography. This was the idea of John Dowling. And hey, this sounds like it could be useful. Sounds like this could be incredibly useful. Well, it's never been made practical, but it sounds like it could be incredibly useful. The idea here is to use entangled photons to form an interference pattern with detail finer than the Rayleigh limit. And in fact, the resolution is of the order of the wavelength of light divided by twice n, where n is the number of entangled photons. So it scales nicely, at least if you do, in theory, it scales very nicely. So here is the conceptual picture of how this works. You take your parametric down conversion crystal, you pump it with a laser beam, you create two entangled photons. These photons mix at a beam splitter. Now, you may not know this, but if you take Jeff Lundin's course, I'm sure you will learn this, that when two identical photons mix at a beam splitter, half the time both photons leave through the upper port, half the time both photons leave through the lower port, but you never get one photon here and one photon here. So you create a two-photon state here or a two-photon state here. So he calls this a noon state. He calls it, it's testing my strength, he calls it a noon state because you either have n photons in mode A and 0 photons in mode B. It's a linear superposition of this with 0 photons in mode A and n photons in mode B. So, of course, this works better if it's a high noon state, which was a movie with Gary Cooper. John's joke, not mine. Okay, so now the idea is that you form an interference pattern here, but this interference pattern is written into a two-photon photoresist. And the nature of the interference, it's not classical interference, it's that the probability amplitude of two-photon absorption, both coming from this beam, interferes quantum mechanically with the probability amplitude of two-photon absorption, both photons coming through this beam. And if you work your way through the math, or even if you just think about it for 30 seconds, you'll see that you get the density of fringes is twice as large here. So I said, I think I am allowed to say that there's been no practical implementation to date. I can say that because I am the author of the non-practical demonstration, which is shown here. You see, we actually did the experiment, and we saw a doubling of the fringe pattern. But I don't think that we will be competing with Intel anytime in the near future using this method. But isn't that neat? Isn't that nifty? You can overcome the Rayleigh criterion using the quantum properties of the light field. Now, another thing that I've been working on is the question of how much information can be carried by a single photon. Actually, this came up in one of the earlier lectures, but here it's coming up in a slightly different context. Here we have an object, and I want to identify what the object is, even though only a single photon is allowed to hit this object. So, and we have to assume that the object is one of a member of this set of 4 different objects. Here we have a multiplexed hologram, so that if the field distribution associated with the transmission through here fell on this hologram, it would fall onto detector A. If the field distribution is that of object B, it goes here, C here, and D here. So how does this work? Here's your entangled photons. I've just drawn the picture like this, so that instead of them both coming like this, one is going forward, one's going backwards. If this photon falls on the object, if some fraction of the time it will be transmitted and this detector will go click. But the 2 photons are entangled. So as soon as you perform a measurement on this photon, you know that the other photon has to be in the same quantum state as the first photon. So you collapse the wave function of this photon to be that of the transmission through this object here. And here we did the experiment. Here's the object, here's the detector. If it worked perfectly, you would get only the peaks on the diagonal. The smaller peaks represent crosstalk. So you see that at like a 95% level, we're able to identify this object with illumination by just a single photon. Okay, so let's now get into another topic that is known as ghost imaging. Ghost imaging was a concept that was introduced by Yanhua Shi at the University of Maryland, Baltimore County, and David Pliszko from Moscow, who was visiting Yanhua at that time. And here is the idea. All of these start off the same way, don't they? A laser beam falls onto a parametric down conversion crystal, and you create two entangled photons. One of these photons interrogates the object that you want to image. If the photon is transmitted, this detector goes click. We call it a bucket detector because it's big. We're not trying to get any spatial resolution of this detector here. The other photon falls onto a photodetector array, and we look in coincidence. It's called ghost imaging because the image is formed at this detector, even though the photons that fall into this detector have never physically interacted with the object of interest. So it works in Baltimore. It works at the University of Rochester. More recently, Miles Padgett has increased the sensitivity and the number of pixels of this object markedly. Well, this is a mannequin, not a person, but it gives you some idea of how far this has come along. So it has some applicability to remote sensing, imaging under adverse conditions. I'll give you some examples as the talk goes on. So early in this game, a controversy arose. And the controversy was whether ghost imaging is a purely quantum process. I said two entangled photons, but then the question comes up, if the photons were correlated, but in a purely classical way, could you still do ghost imaging? 20 years later, common sense says, yeah, there's nothing quantum about this. But there was some raging debate at the time. Some of my good friends at Boston University wrote a paper saying that if you can do ghost imaging, it means that you have implemented a quantum protocol that only quantum states of light can give rise to this. I didn't believe it. I'll tell you more about that. But Gatti, Brambilla, and Lujato looked into this and said, well, their answer, which I agree with entirely, is that you don't need quantum states of light to do ghost imaging. But if you do have quantum states of light, certain features appear that could never appear in the classical version. And one of these is that if you do it quantum mechanically, you have these correlations both in the near field and in the far field. Whereas classically, that can't happen. Classically, you have to focus your camera on what you want to look at. So John Howell, my colleague at Rochester, Ryan Benink, my PhD student at the time, set off to do this experiment. So again, we do parametric down conversion. We have an object which is a two-slit mask. With lenses, we can put the object either in the plane of the nonlinear crystal or in the far field of the nonlinear crystal. And you see that in both cases, we were able to resolve this mask. Now, if you say these results don't look very good, that was the whole point. They were working at the limit of resolution. That if we had things that were clearly resolved, we couldn't have asked the question we're trying to ask here. But then we repeated this with a purely classical type of correlation. We simply had two beams of light that were synchronously pointing in different directions. And we got good imaging in the far field, but not the near field, the way this was set up. So this sort of set the question to rest that both theoretically from Lujato's work and experimentally from our work, that you do not need quantum correlations in order to do ghost imaging. So then what happened next, and people said, well, if you don't need quantum correlations, maybe you can use the correlations that are present in the speckle pattern, I'll call it a speckle pattern, that is present in any thermal light field or quasi-thermal light field. Intuition, these are Hanbury-Brown twist correlations. So if the Hanbury-Brown twist effect works, then we know that there are these correlations in light fields, and it's just a matter of being clever as to how you make use of them. So, okay, so this is the point, is that actually sunlight, if you take a photograph in 1 attosecond, you will see a speckle pattern. It's only because your eye integrates over many, many speckle patterns that you see something that looks uniform. So this whole class of experiments looks something like this. You have a laser beam, you have a rotating ground glass plate, and this creates a speckle pattern. You then go through a beam splitter. This is classical. So when classical light falls onto a beam splitter, you have identical speckle pattern here and here. The CCD camera measures the speckle pattern. This bucket detector sees how much light passes through the object. Now, why does that work? Well, let's just consider a very simple case in which the object that we want to photograph is simply this single slit. And you allow a speckle pattern to fall here, and the same speckle pattern to fall here. And sometimes maybe more light gets through the slit, maybe other times less light gets through the slit. You take the amount of light that goes through the slit, multiply it by what you measure here, and then sum over many, many realizations. And as you sum over many realizations, the object builds up in a statistical sense, because you are weighting more heavily those speckle patterns that are correlated to the object that you're trying to record. Now, is this useful? It's useful for publishing papers in physical review letters. That's our goal in life, isn't it? But how could it be useful in a more general context, in an engineering context? Well, whoever said that the two wavelengths, that the two beams of light have to be at the same wavelength? You can set things up so that the light that illuminates the object is at a different wavelength than the light that falls onto your CCD camera. And this might be useful because visible light cameras are very much more sensitive than infrared cameras. So this could be something of practical use. This is work that I've done with Miles Paget at the University of Glasgow. So it's two-color ghost imaging or wavelength shifted ghost imaging. We do parametric down conversion. We produce a signal at 460 nanometers and an idler at 1550 nanometers. We illuminate the object at 1550, but we allow the 460 nanometer light to fall onto our camera. This wavelength ratio is 3.4. You need an excuse to publish your papers. This was the biggest ratio of wavelengths ever recorded. So here's how the experiment works. Well, the same general concept as before. Here we have some object, which is, well, just a stencil. We have an object. The 1550 photon falls onto the object, and it falls onto a 1550 avalanche photodiode. This is used as the bucket detector here. This detector answers only the question, did the photon get transmitted or did it not get transmitted? if this detector goes click, we tell our intensified CCD camera to capture a frame. Now, the trouble is that it takes 20 nanoseconds. 20? It takes like 20 nanoseconds. You can tell it's been a long time since I've stepped into the laboratory myself. It takes only like 20 nanoseconds to turn this on. After you send it the pulse, it says take a picture. It's like your cheap electronic cameras, especially in the old days. You press the shutter, and about a second later, it takes the picture, and by that time, the subject has moved out of the frame. So we have to have an image-preserving delay line. So you bounce the light back and forth over like a 20-foot path length, but you have to conserve the image information. So it's like the old days where people were building periscopes for submarines. You have to relay the lens, you have to relay the image from one plane to another plane to another plane. So here this is, and you see that it did indeed work. Now, last thing to tell you about, where is this heading? So I want to tell you about an entirely new type of ghost imaging, which I'll call interaction-free imaging. But as a first step, let's just look at it almost philosophically and ask, what constitutes a quantum measurement? So let's say that you have a single photon, it falls on a beam splitter, and the detector goes click. You now know with certainty that the photon left this port of the beam splitter and not this port. But now, let's say that you do the same experiment and the detector does not go click. Well, if you really knew that you had a photon here, that means that you know that the photon went in this direction here. So this is an example. I didn't come up with this. Some very, very well-known people came up with this before me. This is an example of how a non-measurement can constitute a measurement. Even though the detector didn't go click, you know for certain where the photon is. So just keep that in mind. And now let's take a look at what is called interaction-free measurement. So let's of all, this is shaded because it's not really there. Later on, we're going to put an object here. So here is a Mach-Zehnder interferometer, and we have balanced the paths so that a single photon entering here will certainly exit through this port, not through this port here. Now, let's put an opaque object here and think of what happens. The reason you did not get light here before is that you had destructive interference between this path and this path. But if you block this, you no longer have destructive interference. So suddenly, 25% of the time, you get a click in this detector. So putting an opaque object here makes the signal go up, not go down. At the one level, that's obvious, but think of how counterintuitive this is, because you now know with complete certainty that you have an opaque object here, but you also know with complete certainty that the photon didn't hit the object because there's only one photon. If it hit the object, you couldn't have made the detection here. So this has been called interaction-free measurements. Andy White, Paul Kwiat, and others then turned this into a quantum imaging protocol. They put microscope lenses here and here, and then they take some small object and translate it through the focal region here, and they map out the transmission distribution of this object using photons that didn't hit the object. And here are two examples of transmission distributions that they measured using this method. Okay, so now what are we working on here? Well, it's Frédéric Bouchard, Harjapreet Mand, and Ibrahim Karimi. But let me go back first to tell you how the experiment works. So instead of a single photon, we have two entangled photons. The whole ghost imaging story again. One of the photons falls onto a photodetector array. The other photon falls into the interaction-free measurement setup. Now we have a very small object here, smaller than the diameter of our laser beam. If this detector goes click, it means that this photon had hit this object. So the beam was this big. It means that we have localized the position of this photon to a very small spot. Question is, do we also localize the position of this photon that was entangled to the other one? And I think most people would think yes, but you could argue either way. And until you've done the experiment, you don't know really whether you've localized the photon or not. So ask in the language of quantum information, quantum optics, does a measurement here collapse the entire two-photon wave function, or does it only collapse this part of the wave function? Okay, so we did the experiment. I won't show you the setup. It's basically this, but of course much more complicated because we have all the beam splitters and everything else. But we did the experiment. So we have a straight wire is the object we're trying to do. If you look at the singles counts, you just feel the entire field of view. But when you look at coincidence counts, you get an image of the wire here. So so this is about 5 times narrower than this. So this is still another protocol for doing ghost imaging. From a foundations of physics point of view, this result shows that interaction-free measurements lead to wave function collapse, just like standard measurements. But is this useful? Well, we think it is, and we are continuing to work on this. It allows you to see what something looks like in the dark, which is sort of a strange concept, that it's what it looks like in the dark. Is that useful? Well, there are biomaterials that are extremely sensitive. They change their chemical state and perhaps their physical state when a photon falls on it. An example being the retina of the human eye. So here's a way that you can form images. You can form images without the photon ever hitting the object. Now, of course, with a success rate of 25%. So, but maybe that's okay. You have a large number of identical objects. You want to know what they would look like if you looked at them in the dark, and this allows you to do so. Okay, that's the first half of the talk, which is actually more than 50%. Second half of the talk, I want to move on to another topic, and it's one that has fascinated me for a very long time. It's self-action effects in nonlinear optics, and by self-action effects, we mean that a light beam modifies its own propagation. And there's 3 main types of self-action effects that people have identified. There is self-focusing. So imagine a material in which N2 is positive. One of the basic nonlinear optical processes is N is equal to N0 plus N2I, saying that the refractive index that you would measure for a material depends on the intensity of the light that you use to measure the refractive index. And I'm saying let's assume that N2 is positive, which it more often than not is positive. It could be positive or negative, but more often than not it's positive. So you see what's happening here is that the beam is more intense at the center. It increases the refractive index more at the center than in the wings. So this looks like a little positive lens when the light comes to a focus. There's another process known as self-trapping. Here the beam propagates through a distance much longer than the usual Rayleigh range without diffractive spreading. And we can think of this as a balance between the tendency of a beam to self-focus with the tendency of a beam to spread due to diffraction. And there's another process called small-scale filamentation. Under different circumstances, you take a very intense laser beam, let it propagate through some nonlinear material. It will break up into a very large number of little spots. So these are the canonical examples of what we mean by self-action effects. Self-trapping was first described theoretically by Charles Townes and his graduate students at that time. Here was his model. He says, let's remember that in a confined beam of light, there will be an uncertainty in the k-vector. So there will be a spread of k-vectors. Let's argue that the beam will be self-trapped if every ray of light in this bundle undergoes total internal reflection at this boundary. So here I've shown a ray that would not be self-trapped. But if the refractive index difference were a little bit bigger, then this ray of light would be reflected, total internal reflection, and would be constrained to remain inside the spot, this region. So a model that's that simple, then you impose Snell's law at the boundary. You argue that the spread of k-vectors will be something like the wavelength of light divided by the diameter of the beam, and you come up with this result, that there's a critical power there's a critical power that to form a self-trapped filament, the beam of light has to have exactly this much power. Does this make sense? Well, the larger the nonlinear coefficient, the less power you need to establish self-trapping. The larger the wavelength, the more power you need to establish self-trapping. Now, is your cup half empty or is your cup half full? There are some people like me who think that we want self-trapping. This is neat. This is something we want to study. So we want P critical to be as small as possible. But there are other people who want to send huge amounts of power through the atmosphere to get it from one place to another for whatever reason you can imagine. They would like P critical to be very large. So, of course, if the power exceeds P critical, then you get the self-focusing. Go back. So there's a critical power for self-trapping. If the power is greater than the critical power, then this will happen. And unless you want to study this for its own sake, you most likely would want to prevent that from happening, especially because laser crystals tend to be expensive. And when this happens, it almost invariably destroys the laser crystal. Okay, so the Townes argument was very heuristic. How do you study these things mathematically? Well, there's an equation. Both of these are called nonlinear Schrodinger equations. There is a nonlinear term here. This is the paraxial wave equation. This term here describes how the field amplitude changes due to propagation. This term here expresses self-phase modulation, the tendency of the beam to broaden as it propagates. So we understand temporal solitons as a balancing of nonlinearity with group velocity dispersion. For a spatial soliton, well, the equation is of the same mathematical form, except here it's the derivative with respect to the spatial coordinate. But other than that, it's the same mathematical form. So if you can solve this, you can solve this. This is called a spatial soliton, and this is another way of describing what we mean by self-trapping. And here are some of the people who have worked extensively on these processes. Now, can self-focusing be useful? Well, here's an example of where it can be useful. This is called self-mode locking in a titanium sapphire laser. So, historical comment. In the early days of lasers, people worked very, very hard to get their lasers to mode lock. A mode locked laser produces a very short pulse of light. So people would put satchel absorbers into the laser, an electro-optic modulator inside the laser. Wilson Sibbett and his students one day were set up their laser, went out for lunch, they came back, they'd done nothing to it, and was sitting there mode locking. They called it self-mode locking. Here's the model that they came up with. If the laser is mode locked, the peak intensity will be very high. The beam will tend to self-focus. Not totally self-focused, but it will shrink in size. And then the entire beam of light can make it through some limiting aperture in the laser, perhaps even the diameter of some laser mirror. But if the laser is not self-focused, then the peak power will be lower. The beam of light will be cut off by this aperture. So when lasers start up from noise, there are lots of fluctuations. So the fluctuations that allow the laser to reach threshold to begin with will favor this type of high peak power because it allows the laser more readily to reach its threshold condition. Now, the other process that we talked about is small-scale filamentation. And here is the pictorial version here. You have a laser beam, and here's its wavefront. But if you look very, very carefully, it's not really a plane wave. There's always some wavefront modulation on it. If you go through the coupled amplitude equations for propagation through a nonlinear material, you find that this is an unstable solution. You can do a linear stability analysis. You find that this is unstable, that these small irregularities become bigger and bigger irregularities until the beam finally breaks up into different components and looks something like this. And Bespalov and Talanoff worked this out, and there's a transverse k-vector in which the gain for this is maximized. That sets the characteristic distance scale over which this can happen. Okay, so that's a very small introduction to self-action effects in nonlinear optics. Let me just tell you a little bit about things that I have worked on in this field. So this is going back a few years. This was my first PhD student, Donald Harter. Well, we were actually looking at Rabi sideband generation. You take a sodium atom, you drive it with a laser that's so intense that you drive it coherently between the ground and excited state, and you can drive it many times during the laser pulse duration or the relaxation time that you call T2, whichever of those is shorter. So you come up with a spectrum with Rabi sidebands, but what we found is that to get in the regime where you can see these Rabi sidebands,